So 125, let's come back to this. That's a little bit longer.
Yes, for real.
It's got about another half hour of this. So before the break, we had said, okay, you got a basketball, you throw it, right? So it starts at low energy, it goes up. When it's up in the air, it's got high energy. That's why when it falls back down, it's got energy, right? And then you catch it, right? So basketball goes low, high, low. And same thing with your electron, right? Starts low energy, jumps up to the conduction band, right? So high energy, then drops back down to the valence band, low energy. And then I said that this isn't actually what happens. Because we do not live in a perfect world, right? Unfortunately, we don't live in a perfect world. So, let's talk about what actually happens. Let's say that you're playing basketball, right? All right, you're dribbling. All right. You line up your shot. Shoot the ball. All right, no, I'm a pro, okay? Phosphor comes in, hits the net, but it gets stuck and caught in the net.
Oh.
And now everyone's standing there like, well, now what do we do? Right, it's stuck. You got caught in the net got tangled, right? It's not a perfect world, right? So the net gets tangled sometimes. Like, how do we get this basketball off? Is anyone tall enough to jump and like knock it out, right?
Throw another ball in there.
Yeah, sure, throw another ball in there.
Throw a smaller
Right?
player.
So
Hit it from
how, right, yeah, hit it from the bottom, right? Throw a smaller player up short. Okay. So the general idea behind all these solutions though is you gotta use some more energy to knock the ball out of the net, right? So, right, we toss the basketball and oh no, it's not coming back down. It's stuck in the net. Whatever shall we do, right? So then, right, this player goes in, pops the ball back out, right? He needs to use a little bit more energy to jump in, knock the stuck ball out of the net, and then it can fall back down.
Okay.
Does that make sense? You can imagine that? Same thing happens for your electrons.
But the basketball player made a mistake. He should hit on the top, bring it down
No.
inside the basket.
No, the net just gets tangled sometimes. That's just life. That's just how it is. So, the phosphor layer has defects. These defects in the phosphor layer are called electron tracks. Why do we not get rid of these defects? Because we want them. These defects are useful. Why? Because X-ray comes in, excites the electron. Electron jumps up into the conductive band and gets stuck. It wants to get rid of its energy and drop back down, but it is not allowed to. It is stuck up here in this high energy state. And so,
You said a phosphor layers have defects which are called what?
electron traps.
Electron.
So now it's stuck up here. It's been caught inside this electron trap, which is a good thing. Because if it dropped back down immediately and it gave off light immediately, well, it's still stuck inside your bug key. You still need to take the plate from your bug key and bring it to your reader. It's too late. The glowing already happened. You have nothing. But if they are trapped, they're stuck in that high energy state, that gives you time to walk over, take the plate, bring it to your reader, and then when they relax, the light gets given off, you collect the light, and you create your X-ray image on the computer. That is why this is important. So X-rays come in, electron gets excited, jumps up to the conduction band, tries to fall down, gets caught inside the electron trap, and it stays there. It stays there for up to 48 hours.
Oh wow.
And so, inside our reader, when we take it and we stick it inside, what's going on? A laser comes by and scans your phosphor. And when the laser hits the electron, the laser gives the electron enough energy to pop back out, and it gives off light in the process. And that light is what we use to create our final image. So these electrons trapped inside the conduction band, those electrons are basically our latent image, our invisible image caught inside the PSP plate of our CR cassette. Does that make sense?
Yeah, repeat that one more time.
So we've got these electrons caught inside our PSP plate now, right? The areas that got high exposure, lots of electrons will be trapped. Areas that got low exposure, not very many electrons will be trapped. And so these electrons basically create your image. These electrons are your image, but you can't see them. So they are your latent image, your invisible image. When they glow, that's when we start to create our manifest image. Why do they glow? Laser comes by, knocks them out, and they give off light. So let's see, Jay had to stand up first.
I have two questions. First, the light photon that is released is then captured by the photodetector.
That is, yes.
And then that forms our image.
Correct.
Second question, so how many, so we've got two instances now. The first one you showed us the theory, right? Theoretically. Second was this one. How much of the electrons get trapped? Or
How many of the electrons get trapped?
because the way that you explained it made me think that like the electrons get shot up into the conduction band and they come right back down. So we aren't getting any of those photons that were released, or that were, are they not useful?
Right, so the ones that don't get stuck in the electron traps, those do not help create the image.
Okay.
Only the ones that are in the electron traps will create the final image. What percentage of that is it? I don't know. I don't think your book mentions it.
Okay. 'Cause
1%.
you know how we have like 99%
It says
heat.
1% found,
That's what I'm-
forms the
Right,
laser.
I did not see a number inside your book.
Okay. So we're still, despite the X-rays being shot, we're getting a percentage of the 1%,
Correct.
and that's what we're talking
That's
about.
correct. We're getting a percentage of the percentage of the percentage.
That's what I thought.
Yes.
So,
Melanie. Okay, Saki.
so what is this laser?
This laser is inside your CR reader. So you know the thing that you stick the cassette into? And it goes ka-chunk and it's like chunk, 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 chunk. Right? Inside, that's what's going on. You've got a laser that is scanning the PSP plate.
Oh, so this is when we bring it from the patient after taking the X-ray and put it in the CR reader.
Correct. The CR reader or the CR processor.
And the laser goes, once you start that, the laser gets shot towards the plate.
So the laser shoots at the PSP plate, it scans it back and forth, and it releases these light photons.
Thanks.
It releases the electrons which give you the light photons.
So the laser has enough radiation to relax the electron?
It has enough energy to give them, to pop them up these traps and relax them, yes.
But the laser itself doesn't provide the photon. It doesn't provide the energy for the photon.
Correct. The laser is not the one creating the photon, the laser is not the one
It just
moving
re-
it between bands, right?
It releases the photon from the electron though,
It just releases the electron from the trap.
from the trap.
And then the photon comes from the electron relaxing back down.
Okay, so there's two separate processes.
Any other questions about this?
You said something about relax. What's going on? I wrote it down, but I don't know what I did.
So by relax, all
Yeah.
I mean is that conduction band is high energy,
Uh-huh.
valence band is low energy. Right? If you're going from high energy to low energy, you're relaxing, right?
Okay.
Right? You're all pumped up, and then you calm down, right? You relax, and now you're low energy. Right? But that energy has to go somewhere in physics.
Mm-hmm.
So what happens to the energy? It gets packed up into a cardboard box and shipped off as a light photon. Right? That's where that energy goes. This is how the phosphor layer works. This is how the phosphor layer captures your latent image, and then how we get a manifest image out of it. Oh, okay, sorry, I dropped a number.
Aha!
Okay, so about half the excited electrons end up trapped in the conduction band. About half of our excited electrons end up trapped in the conduction band. What's the purpose of our europium activated barium fluoro halide, or the europium activated part? The europium
Makes it
helps
glow.
to trap the electrons. Right, so in the end we'll have more glow, right? More trapped electrons means more glow
More light.
once we get to the reader. Yes, Jay?
So now we're only getting 50% of the 1% that we're getting of the X-rays.
Yes.
Is that going to be a test question now? So now, like of the 99% heat, how many of the X-rays?
I'm not gonna ask it.
Okay, cool.
Go ahead, Melody.
The percentages is throwing me off. What is what and what is what?
So right now they're talking about all the way back in the tube for X-ray production.
Useful
When you
X-rays.
go to the tube, you have the filament and the target. Right? So you shoot electrons across from the filament to the target. Of those electrons that hit the target, 99% of those electrons only produce heat. Only 1% of those electrons actually will produce X-rays. So that's what the 1% was about. So Jay is just saying that it's a very inefficient process. Because now of those X-rays we produced, only 50% of them will actually create the image on our PSP plate. Right? Half of them will immediately cause electrons to get excited and relax, and we can't capture them, right? They just excite, relax, while it's inside the bucket. But the other half will excite, get trapped, and once they're trapped, we can bring it over to the reader, stick the cassette in, it pulls out the PSP plate, runs the laser over it, and that will give us our image. So about half the electrons will get trapped, and those are the electrons giving us the image. Right, so those electrons make the latent image. Once we collect the information from them, then we can make our manifest image. Manifest image is the image that we can see. Are we okay with this?
So, the europium activated barium fluorohalide is both conduction band and the other
Correct.
one?
Those energy bands are all part of the
same
europium
thing?
activated barium fluorohalide.
Okay.
Okay. The trapped electrons are proportional to exposure of X-rays in the area, right? So like I said earlier, if more X-rays expose it, more electrons get excited, more electrons get trapped, right? So if it's an area with air, right? If it's the lungs, lots of X-rays go through, lots of electrons get excited, lots of electrons get trapped. If it's something that's bony, like the spine or the pelvis, right? X-rays go through, they get absorbed by the bone. Very few X-rays reach the IR, right? Very few reach the PSP plate, so not many electrons, not much gets trapped. Right, so the parts where we have got a lot of electrons, that's the highly exposed area. The part with only a few electrons, that's the part that didn't get exposed, right? Lots of absorption instead. And so that's how we can see the differences in those body parts, right? So once the light releases, that part will be black. Over here, it's going to be white. Right? The laser is what gives the trapped electrons the energy needed to escape. This light which is given off, this light is called photostimulable luminescence. We already talked about photostimulable, right? Right? Able to be stimulated by light. In this case, the laser. Right? Luminescence, what does that mean?
Light.
Light.
Right,
Ability
light,
to
glow. Right,
The
so
emission of light.
the light released is the glow caused by excitation from the laser. Photostimulable luminescence. So the photostimulable phosphor has photostimulable luminescence. Photostimulable. Stimulated light. Light stimulates it, light comes out.
So this is the light release.
Right? So laser energy goes in, light energy comes out. And so, the phosphor itself can be set up in two different ways. One way is turbid. So our phosphor crystals, our barium fluorohalide, is arranged randomly. The other one is structured, where it is formed into columns. The difference is that if they're arranged randomly, the light which is produced can spread in all directions a lot easier. If they're arranged into columns, it actually kind of directs the light along the column. So it keeps the light from spreading out as much. That means you would actually have better spatial resolution because the light only travels in straight lines rather than in all directions.
You said the light travels where?
So in structured,
Mhm.
the light travels along the direction of these columns. In turbid, the light travels in all directions.
Thank you.
All right, so we're pretty much done with talking about the phosphor. Any final questions about the phosphor before we move on?
Let me breathe.
Okay.
So the structure of the phosphor and the turbid phosphor is the type of thing that you'll buy, or is it present in all PSP plates?
So it is how how the PSP plate is designed. The PSP plate is going to be either turbid or structured, one or the other.
And which are the ones that normally what we are using, sir?
Turbid's probably cheaper, so I'll guess turbid.
So where does that laser come from usually?
Yes.
Inside
You said something else, but I don't know.
of the reader.
Good. Ah, great. So where does that laser come from? Yes, it comes from the processor. It comes from the CR reader.
Okay.
Oh, yes.
The laser comes from
The laser will come from the CR reader.
which releases those trapped electrons.
It releases trapped electrons.
Wow.
That's right. Start to connect it. Start to connect it.
Laser.
Comes from the CR reader.
We'll talk about it again.
And the laser message is only created by the trapped electrons, right?
Right, the trapped electrons that read your laser data.
Because they release light energy.
So it's because you can't see it, right? Latent means invisible image.
Okay, the laser comes from your reader and that releases the electron.
That's right.
With that
Trapped
looking up
electrons.
there,
It has to be
which one is this
The
one?
electron stuck in the conduction group.
Which one is the one on the left?
The one on the right is the column one on the
That
left is
creates
that
light.
revival
Do you remember the terms?
strength.
Don't look up there, don't look up there.
Turbid and
Okay.
I saw it
Yeah,
already.
that's fine.
All right.
Structure.
Anyone else still need to slide, or can we move on?
I'm gonna ask again. Ask again.
Right. So let's talk about the CR reader. So, all right, we've got our cassette, right?
Did you make that?
I made that, yeah.
Cute.
Thank you. Okay, so
That's that color cassette.
the reader will pull the PSP plate out of the cassette, right? So it goes zoop. It pulls out the PSP plate.
Oh, that's what it
While
does.
it's inside.
Oh,
Yeah. So the reader latches onto these two things here, does that, pops it open, sucks it out here,
Oh, raise it?
puts it through a roller system, and that brings it over to the laser. So the reader is going to scan this PSP plate with a laser. Okay, once again, the laser is going to free those trapped electrons.
Mm-hmm.
The electrons inside the conduction band. When that happens, right, those electrons will release light photons, right? That release of light we call photostimulable luminescence when they go from the conduction band back to the valence band. And so the laser is going to go back and forth, right? It's going to scan like this, back and forth. This is called the fast scan because it goes back and forth fast. At the same time, this PSP plate is going to get fed slowly this way, right? So it's going to scan, 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 scan. It's going to scan the whole thing. So this motion, as it feeds forward, is called the slow scan. Okay. So we've got the fast scan, and we've got the slow scan.
Okay.
Okay.
So this is all happening like at the same time as the PSP plate is getting pulled through by the reader.
So it gets pulled out, goes through some rollers, goes scan, 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 and then it gets shoved back inside your cassette.
So this happened when we put it in there.
Mhm.
See here? Oh, that's where you hear all this noise.
Why is this going fast,
Mhm.
but when was this going slow?
Correct.
Also, it's the slow scan is moving it back inside the cassette.
So the slow scan, think of it like a conveyor belt, right? The conveyor belt is the slow scan, right? Things are moving slowly along the conveyor belt. As it moves along the conveyor belt, you're just scanning like this. You're like doing that, right? Or it's like, here, let me borrow someone's book, right?
You see, I hate them.
Are you okay?
I hate seeing them.
All right, don't just volunteer someone else. All right, let me just borrow this book. All right, so got a book, right? So it's like if I was blocking off at the top line, right? So how do you read?
Just read the top line.
Right, so you read the top line and then next line, right?
Go down.
Right, so as you're reading the sentences, that's your fast scan. Right? As we keep moving and revealing more and more sentences, that's your slow scan. That's all that's happening. Fast scan is you reading across, slow scan is it
That's
slowly
good.
revealing everything.
So until you showed it like this, I didn't understand what slow scan
But
was.
that's what I'm here for.
Might I suggest?
Yes.
So I guess next time, like when you're showing this one, do the Star Wars credit scene, like the
Okay. Yeah, that makes
a
sense.
long time ago.
Yeah, it's like the Star Wars credits.
Yeah, it's like that.
Long time ago, right? In the galaxy far, far away.
Because you know sometimes if you're speeding up,
They also have to
can't read
learn
that
about
fast. Slow down.
And this is what?
So this is inside the CR reader. This is inside that giant contraption that you stick your cassette into.
I have a
But
question.
that's interpreter.
Why does it take a long time to read like a lateral lumbar spine? Because like when we had some of those exams and the tech was like, I don't know why it takes so long just to process the lateral. So is it because more?
I don't know. It's hard to say. Could be a variety of reasons.
Upgrade?
Wouldn't it be trabecular detail? Like it's trying to get all that stuff?
So it could be
They're
that
drilling up there.
for a specific exam, the laser moves slower than normal. And we'll learn later that depending on how far the laser moves, that will determine the size of our pixels.
Oh, the pitch and all that.
So yes, pixel pitch, and so that will determine your spatial resolution. So could be something like that. Not sure. Or maybe the machine just decides to die every time it's a lateral lumbar. And it's bad luck. Okay. So now that we've collected light, right? Now that light is coming off our PSP plate, we need to do something with that light. We have to do something with this photostimulable luminescence.
Yes.
So what happens is we've got these fiber optic wires, right? We've got these wires made of glass. And these wires will capture the light and feed the light to a photodetector. A photodetector is a very fancy name for a camera. This is basically a camera. It takes in light and it creates an electronic signal. It turns light into an electronic signal. And so the electronic signal is something the computer is able to use. Right? Computer doesn't take light as information. Right? You shine a flashlight on the computer, nothing happens. But you give the computer electronic information, and now it can do something with it, right? So we have to turn the light into electronic information. That is the purpose of our photodetector. Okay, so light goes through our fiber optic wires made of glass, and then that goes to our photodetector. Any questions here? Yes, Jay.
So when the photons are released from the conduction band, they go here.
Mhm.
Where do the mirrors come into play then?
The mirrors. Good question.
For one of the.
Let's see, where do we talk about the mirrors? It's going to be later. We'll talk about that later.
You read.
How far later? Yeah, the mirrors are really fun to talk about.
The oscillating mirror and then the rotating mirror?
Yeah, that's going to be near the end. of
Part
this.
2.
Yeah, that's going to be near the
That'd
end.
be part 2. It's
All
part
right.
2, ain't
Dude, I'm fucking
So-
dead. I'm so mentally
Alright.
done.
Light goes through the wires, gets captured, and so the photodetector turns light energy into what we call an analog electric signal. Okay, so it's analog right now.
it? Analog.
Can you go past
Analog being ones and zeros?
fiber optic wires?
Yes.
You're still where?
This is all inside the CR reader. All of this is inside the CR reader. So analog is the opposite of ones and zeros. Analog is your, and digital is your ones and zeros. They're digits. Ones and zeros are digits. That's why it's called digital. So we need to take this analog signal, which the computer cannot understand, and we need to turn it into a digital signal, which a computer can understand. Computers understand digital stuff. They do not understand analog stuff.
So then is analog like wavelength and frequency, or like how does that work?
So analog is something that's continuous, digital is something that's discrete.
Okay.
So, in order to turn something from analog to digital, we use
A converter.
ADC.
ADC, analog to digital converter. This is probably the most straightforward named item in the entire chapter.
Or-
It tells you exactly what it does. Oh, okay, fast and slow. That's
The
pretty-
whole book.
Yeah, that
Really.
makes sense as well. Right, but analog to digital converter, it literally tells you it's taking something that's analog and converting it into something that's digital. It's ADC, analog to digital converter. And finally, that digital signal gets sent to your computer, and the computer turns that digital signal into an image that pops up on the monitor, and you finally have an image. What kind of image? Manifest. You finally have your manifest image. So that is the process from start to finish, from a photon entering the IR to the image coming up on the screen. Like that was what we discussed all the way back here at the beginning of class. Right? X-rays interact with the phosphor. Excited electrons are trapped in the conduction band. The laser releases those electrons. The electrons give off light. The light is captured by the photodetector, which sends the analog signal to the ADC, which turns it into a digital signal, which gets sent to the computer. We covered the entire thing.
We did good.
And that is how it works.
So how would you simply explain analog, sir?
So analog is an electric signal that a computer cannot use. Digital is a signal computer can use.
So analog is an electric signal also, sir.
It is
It's
an electric signal.
continuously.
Yes.
Hold on, I don't know my question.
All right, go ahead and keep thinking. So, we have finished CR today. Next time, we are going to talk about DR, direct radiography. Under direct, we're going to go through this same process. How do we go from the X-rays entering the direct plate to an image on the computer, right? So we're going to learn about different things. We're going to learn about scintillators. We're going to learn about CCDs. We're going to learn about CMOS. We're going to learn about TFTs. We're going to learn about photodiodes. We're going to learn about photoconductors. Right? And so, right, like I told you, this is a tough chapter because you have all of these items that you need to know. You have all of these materials that are used to make the items that you're going to be asked to know. Right? Do you still remember what a PSP place phosphor layer is made out of?
Yeah, the Euro.
The Euro something, right?
European.
Right? You need to know that.
Barium, fluoride, hide.
Yeah,
So,
I got it.
make sure that you do look over this material. Make sure you look over this material. Right?
You said
This
the
is
back helps.
Trap the electrons, that's right. Okay, so this is not a chapter you can cram for. I hope that is obvious by now, right? If you expect to cram for this chapter in like 2 days, that is not happening, right? That is probably not happening. This is something that takes time to think about, right? You need to go over this again, and again, and again, and again. So like I said, make sure you are putting in the effort for this chapter. This is why I split the chapter into 2 parts, right? Because otherwise this would be a very, very, very long chapter. So, today we covered CR. On Wednesday, we're going to cover DR. We're probably going to take until Friday going over DR. So make sure that you look over this material because you do not want Wednesday to be the first time you see some of this material, right? You don't want Wednesday to be the first time you encounter a CCD or a CMOS or a scintillator and you're standing there like, what on earth is Mr. Phung talking about? Right? You want to at least have read over it, right? Do your flashcards, right? Go back, look at that vocabulary, so that at least when you come to class on Wednesdays, it does look familiar. I'm glad that they waited until the end of class to start working.